Hello everyone, welcome to this video. We are going to talk about RNNs, which use hidden state, compared to transformers, which use attention. So, when order matters in our data, such as translation, at the county fair, Judge Jamie's fair, we can use either RNNs, which use hidden state, which can be thought of as memory, as we can see here on the lower left-hand side, or we could use transformers, which use attention. Attention can be thought of as measure similarity for words to get context-aware word embeddings, as you can see here on the bottom right-hand side. A quick review on RNNs. Hidden state can be thought of as memory. The hidden state is updated using the current input, the past hidden state. So to calculate hidden state 4, we need to calculate hidden state 1, then hidden state 2, and then hidden state 3. This means that RNNs have a weakness. In a sentence, a RNN has to process the words one by one to calculate hidden state X and cannot process all of the words simultaneously. Another weakness of RNNs is that they are at risk for vanishing gradients, so long sequences become an issue. As we talked about earlier in the course, LSTMs alleviate vanishing gradients, but still do not get rid of vanishing gradients. What about transformers? They use attention. Attention does not use a hidden state. And a benefit is that in a sentence, attention can measure the similarity for all of the words simultaneously and is not forced to measure the similarity of the words one by one. Measuring the similarity for the words in a sentence is not affected by distance, which is another benefit of transformers that use attention. And what do I mean by this? Let's say I have this example sentence. I would karaoke often at the local park during my free weekends. I have gotten better at blank. Hopefully, you should know that the answer is singing. Despite the fact that I put so many filler words in between karaoke and singing, hopefully your eyes focused on the word karaoke, so you should know that the answer was singing. Now, all of these filler words we have right here will make it more difficult for a RNN to know karaoke and singing are similar. However, it will not make it more difficult for attention to measure the similarity for karaoke and singing. This means attention not affected from vanishing gradients when working with long sequences. So again, a RNN has to process the words one by one. So for Judge Jamie's fair, because we're doing all these hidden state calculations, the RNN has to process the words one by one, whereas attention can measure the similarity for all the words simultaneously, as you can see here, 16 attention weights. And obviously, words one by one is less efficient for training compared to for all the words simultaneously. This parallelization means that transformers can have faster training, large models, and these large models lead to amazing performance. As for long sequences, RNNs at risk for vanishing gradients, long sequences become an issue. Attention not affected from vanishing gradients when working with long sequences. So in summary, transformers have better performance than RNNs when working with long sequences. So far in this video, it really does seem like attention used by transformers is better than hidden state used in RNNs. And yeah, it's just straight up better. But there's a hidden downside to attention. And that downside is computational cost. And when talking about computational cost, we'll say n equals the number of tokens, and here n will be equal to 4. We're going to process 4 tokens of Judge Jamie's fair, one using a RNN and another using a transformer. So the computational cost of the RNN is O of n minus 1. When processing Judge Jamie's fair, let's say we do 3 operations. One computer operation, the second computer operation, and the third computer operation. So computational cost of O of n minus 1 4 minus 1 is 3 operations. Whereas if we process Judge Jamie is fair using attention in a transformer, we'll say the computational cost is O of n squared. 4 squared is 16, 16 operations for 16 attention weights, and there should be 16 arrows in this diagram here. So as you can already see, attention has a way higher computational cost than hidden state, 16 compared to 3 operations. And if the tokens in the sentence gets even higher, like 100 tokens, a RNN would have to do 99 operations, and a transformer would have to do 10,000 operations, right? 100 squared. Now, despite transformers having significantly worse computational costs than RNNs, a transformer's significantly better training efficiency and better performance when working with long sequences have led to transformers replacing RNNs for sequence to sequence. That being said, attention's worse computational cost does have some issues. First issue is max length. While transformers are great with working with long sequences, transformers will often set a max input length of, say, 1,000 or 2,000 tokens as a simple example to limit the computational cost. Another issue is high electricity use. Transformers require a lot of electricity, which will cost you more money. Okay, so here's a table summarizing everything we talked about in this video. Despite RNNs and transformers having significant differences, they have the same goal in mind: process ordered data. It's just that RNN will process it using a hidden state, and transformers will process it using attention. Transformers have better training efficiency, and they are better with long sequences. However, RNNs have a cheaper computational cost. If I had to simplify this down to the bare basics, think of it this way: transformers are better than RNNs in so many ways, but it's going to cost you more. Okay, that's it for this video. Thanks for watching.